there. What does that mean? Turning points. Max and mins. Because the math way of saying a max or min is a local extrema point. And since we're in pre-calculus now and not algebra 2, we like to use the correct math terms. And at most in zeros. And that's actually like the fundamental theorem of algebra, that degree in tells you how many zeros it could have. At most n minus 1 turning points, that's kind of nice when you're graphing it, because if you know it's a degree 3 function, an example here, a degree 3 will have at most how many max or mins? N minus 1. It's always 1 less. So a degree 3 function will have at most 2 turning points. And so when you're making that graph, if somehow you get more than 2 turning points, then you know something's wrong. Also, if you find those 2 turning points, you're done with the problem. You don't have to go from there. And also it has at most n zeros. What's a 0 on your graph? Where it crosses the x-axis. So zeros are like x-intercepts, and I hope that we're all aware of that. So if you know the x-intercepts and you know how many turning points it has, just by looking at the degree, you already have a good start on that graph. So that's kind of a nice thing, right? Let's graph one of these. This is the first problem on your homework today. Well, not this exact problem, but the same idea. It says describe how to transform f of x equals x cubed. This is like what we did on our last test, right? Into g of x equals 2 times x minus 3 cubed. And then sketch the graph and give the y-intercept. We're not graphing anything crazy today. All the ones I'm giving you on your homework to graph should be ones you can graph using the transformations. Eventually, we're going to graph ones that aren't easily transformed. Like maybe tomorrow. Just how it worked out. If it wasn't for the NHS and the field trip, we would have been doing group worksheets tomorrow. But we kind of got pushed back because we lost a day.
We're going to do on Monday? That's not a bad thing.
Like my plan book says group work tomorrow still, because I had it planned that we were still going to do a new lesson on Monday, but then like so many more absent, I have to send it out. Okay, so first of all, what does this graph look like? F of x equals x cubed. Yes, like an S shape, one side points up, one side points down. Very rough sketch here. I could say start to 0, this side goes up, this side goes down. It's always my example for an odd function. What's happening over here? It says describe how to transform. So they want words here. What does this minus 3 on the inside say I'm doing? Well, I'm going to move right 3 units. And the only other thing happening here is that 2 multiplied in the front. What does a 2 multiplied in front mean that's happening? Yeah, it's going to be, and actually I could even say it's going to be a vertical stretch. It really doesn't, but I'm just telling you. By a factor of 2, which means it's going to be twice as stretched out than the normal graph. Again, to graph these, you can always just pick a few points. But hopefully we can use these transformations to help us a little bit. So let's see if I can make a graph here. The nice thing when you know x cubed, the same thing with x squared. X squared, you know it's the same on both sides. X cubed, it's the exact opposite on both sides. So if you know one side, then you just make the other side negative. So just like a parabola, I start at the vertex. When I'm graphing x cubed, I like to start right here at that 0.00, like the turning point where it changes, like one side going up, one side going down. Normally I start at 0, 0, I'm moving to the right, do you agree I can just move over 3 units and that should be where that starts? If you're not sure about that, you could check it very easily. If you made an XY chart and you plug 3 in there, do you agree you're going to get 0? Yeah. If you want to think about doing this without an XY chart, normally when you plug 1 into x cubed, you go over 1, how many do you go up? Up 1. Like normally when you plug in 1, you get 1, right? So on this one, when I go over 1, I'm not just going to go up 1 because I'm stretching it by a factor of 2. What should happen is I should go up 2. And because it's an odd function, when you go back to -1, you go down -1. I should go down to -2. And again, you could check that if you want. Like if I plug in 4 here, I'm going to get 1 times 2, which is 2. So it does work out that way. We could go to the next one, but since we know the shape, I don't think we have to. Because what happens when you plug 2 into this one? You get 8. So if we multiply that by 2, what's going to happen if we go over 2? We're going to have to go up 16. I don't want to go up to 16 on my graph, but just know it's going to go pretty fast. So when I make this, I'm still going to make that kind of S shape, but I'm just going to kind of try to make it stretched out a little bit more. You don't need to make giant numbers on your graph. And I think I just gave you maybe even just one of those on your homework today. It's not bad. The other thing I want to focus on today is in behavior and finding the zeros of these functions without looking at the graph. And so we're going to make a little chart here about in behavior. Yes. Yes.
So that equation, right, g of x,
Uh-huh.
would that be a degree of 3?
It would be a degree of 3, which means it has at most, doesn't mean it has to have, at most 2 turning points. How many does this one have? Does this have any max or min points on it? It really doesn't. But it could have, because it's a degree 3.
How many solutions do it have?
And it has at most 3 zeros. How many zeros do we have on this one? We're not going to get to this for a while, maybe until not even until after our next test that we have. But if it has 1 0 where it actually crosses, what does that mean that it has? Because it really should have 3 altogether. What are the other 2? Imaginary roots. So, and then that's the fundamental theorem of algebra. We'll get there eventually. Because it's degree 3, you're right. It really should have 3 solutions, but it doesn't necessarily mean all 3 are real solutions. So this one only has 1 real solution, and then the other 2 would be imaginary solutions. Okay? And that's where stuff's coming back from last year, I think. Okay. Let's make a little table here about how to tell the in behavior of a function, and this is what I call the leading coefficient test. And as we do this, you're probably going to maybe, hopefully, kind of remember this. But based on whether your function has an even or an odd degree, and whether the leading coefficient is positive or negative, you can tell by just looking at that what the end of the graph is going to look like. Which means, are the arrows going to go up towards infinity, or are the arrows going to go down towards negative infinity? And again, that's a nice thing when you're making a graph. If you know the end behavior, you know how that graph's going to end to begin with. And so I kind of wrote this out here again, meaning if this is a polynomial function, n would be my degree, the highest exponent. The number in front of that, a sub n, would be my leading coefficient. And so when I make this little table, I talk about n being the degree, and then I just said leading coefficient instead of the a sub n there. And when your degree is odd, do you remember how the arrows will always end up, like what your 2 options are? think I should start with even because that's the easiest one to think of x squared. But think of the one we just graphed. We just graphed an odd function, x cubed. The arrows went opposite directions. For odd functions, the arrows will always go in opposite directions. It just depends on whether the leading coefficient is positive or negative. So if the leading coefficient is positive, I'm going to draw a little picture here, and then I'm going to actually write it out the way that you should write it out when it asks you on your homework. But if I have a little graph here, if the leading coefficient is positive, the right side of the graph arrow will go up, and the left side of the graph arrow will go down. And the way we write that out very nicely, we say as x gets bigger and bigger and bigger, so we say as x goes to infinity, x arrow infinity sign, we want to know what's happening with my graph, which means what's happening with the y value. So we say as x goes to infinity, f of x, which is my y value, it's getting bigger and bigger and bigger, so it's also going to infinity. Remember doing this last year? I wrote it out just like this last year too. So as x gets bigger, y gets bigger. But on an odd function with a positive leading coefficient, if you look as x goes smaller and smaller and smaller, so we say as x goes to negative infinity, f of x, which is the y value, is also going to go smaller, smaller, and smaller. It's going to also go to negative infinity. Every single time on these problems, when they ask you for the end behavior, this part is going to be the same. The only part that changes is what's happening with the y value. So as you write this a few times, as we do a couple examples, you're going to get really used to saying as x goes to infinity, f of x goes to, and that's what you're trying to figure out. If the leading coefficient's negative, all that is happening is the arrows are switching places. So now, if I draw my little picture, now as x gets bigger, my y values are actually getting smaller, so the arrow is going to point down on the right side. And as x is getting smaller, the arrow is going to point up. When you're just graphing this, this is kind of the visual that I want you to think about. When the problem says describe the end behavior, it's not okay just to draw the picture. You have to give me the math way of doing it, which is this part. So that's why I'm writing it out. So I can say as x goes to infinity, f of x goes to, and as x goes to negative infinity, f of x goes to. That's the part that's the same every time. I always remember odd makes sense that the positive side would go positive, the negative side would go negative. But when the leading coefficient is negative, it switches around. So now the positive side is going to go to negative infinity, and the negative side is going to go to positive infinity. Odd is always going to have a different answer here. Like they're never going to be both going to infinity, both going to negative infinity. And we can do the same thing with even degree functions. And again, even degree functions, hopefully you remember or think about parabolas. For every x squared function, those arrows always either both point up or they both point down. And so when you have an even degree function, your end behavior is always going to be the same, both going to infinity and negative infinity. And when the leading coefficient is positive, think about x squared. How do my arrows look when I have x squared? Both pointing up, which again I think makes sense. A positive leading coefficient, it makes sense that the end behavior, we don't know what's happening in the middle, but the end behavior, both arrows are going to point up. So I can say as x goes to infinity, f of x goes to, and as x goes to negative infinity, f of x goes to. That's just kind of the shorthand way of saying as x is getting really big, what's happening with my y values. And since they're both pointing up, it should make sense that we're just going to put that both of those are going to infinity. And think about negative x squared. When you put a negative in front of x squared, it means it flips over. So when you have a leading coefficient that's negative, both arrows are going to point down. Again, why is this helpful? When you're making a graph and there's a whole lot of stuff going on in it, if you know the end behavior, it's really nice to make sure that it matches up with what you get. So I could say as x goes to infinity, f of x goes to, and as x goes to negative infinity, f of x goes to, and both of these would be going down, so they would both go to negative infinity. Part of your homework, a couple different parts of your homework say describe the end behavior. I want to see those infinity things. I don't want to just see a picture when it says describe the end behavior. Okay? All right, here's something that we haven't really ever talked about before. Also another little piece of advice for when you're looking at graphs. It says that if you have x to any integer power, so any polynomial function there, if your degree is even, think about x squared, that's one we think of the most. X squared doesn't actually cross the x-axis, it only touches it. That works for any even degree function. We're going to talk about that a little more tomorrow, something called multiplicity. But if your degree is even, it's only going to touch the x-axis, and I'm going to just draw you a little picture over here, like this. And if your degree is odd, every odd x power, x cubed is the easiest one for us because that's the one you should know what it looks like. But any odd degree function, it will cross the x-axis at that 0 and not just touch it. Again, nice thing to know when you're graphing some crazy problems, that you can tell right away what's going to happen with that. And you can sketch it without picking many points. This is going to come into play a lot more tomorrow when we graph. Today I just wanted to kind of give you that. Today, besides the end behavior, here's the other stuff I'm going to give you. I'm going to ask you to find the zeros of something like this. It says find all zeros and describe the end behavior. F of x equals x minus 1 times x plus 2 times x plus 3. Do you know how I find the zeros of this? Yeah, you just set it equal to 0, and the ones today are all going to be ones that you can work out. Because what happens if you have a bunch of factors multiplied together and you set it equal to 0? Yeah, it's already factored out for you here, which means you can kind of just tell me, I could set this equal to 0, but I probably don't even have to do the work there. What value is going to make this factor go to 0? Which means x equals 1 is a 0. And this one I'm going to get x equals negative 2. And this one I'm going to get x equals negative 3. The reason they're all going to be like this today is because we haven't talked about how to solve something that's to the 3rd power or the 4th power this year. We did it last year. We're going to do it again this year, but we haven't talked about PRZs and synthetic division and all that fun stuff yet, right? So today they should be pretty easy. You also want to give me the end behavior. You got to know the degree and the leading coefficient. Can you tell me what the degree of this problem is? 3, right? Because you got to think about if you multiply this out, do you agree that you would end up with x times x times x? So you'd have x cubed as your biggest term in there, your biggest degree. So you got to think about that a little bit when you're doing it. But if it's x cubed, could you tell me what the end behavior is that goes with that? I'll fill out this part and then we'll see if we can fill it in. As x goes to infinity, f of x is going to go to something. And as x goes to negative infinity, f of x is going to go to something. And what is this, even degree or odd degree? Odd, which means these should be different when I write them. One should be infinity, one should be negative infinity. How do I know which one it's going to be? Based on what determines which one goes where. The leading coefficient, and the leading coefficient in this one happens to be 1. So as x goes to infinity, f of x goes to infinity, and as x goes negative infinity, negative infinity. Feel okay with that? That's really the majority of your homework today. Finding the zeros when it's factored.
Well, it's like those, not all of them are factored out, I know, right?
Today they are, because we don't know how to solve them. Well, if it's higher than degree 2, it is. Let's try one more here. And you try this one for a second. I'll give you a couple minutes. First of all, you could do the zeros. Remember, it's going to be factored. Just set them equal to 0. And then I want you to think about what would the degree of this one be and what would the leading coefficient of this one be without having to actually multiply every single part of that out. Do you agree with me on my zeros there? I'm going to get negative 1/2 and 4. Now then in behavior, again, you got to think a little bit. We got to think about what would be my highest power of x if I multiply this all out, and what would be the number in front of it. So think about if you were going to multiply this out, you'd have to deal with this x minus 4 to the 3rd power first, right? Which would really be x minus 4 times x minus 4 times x minus 4, which would be a big bunch of stuff. But what would be the highest x in that one if you multiplied it out? Do you agree that I'm going to get an x cubed, because just like up here, we'd have x times x times x, and then a whole bunch of other stuff involved. So now I have x cubed. Then I also would have to multiply that, FOIL that out with all that. But again, just look at the biggest ones. If you took 2x times x cubed, your first term, your leading coefficient, and your degree would be 2x to the 4th. Do you agree with me on that, on how I'm getting that without actually having to multiply it all out? So now, that's even degree, positive leading coefficient, so what are you going to put over here? Okay, they're both going to go to positive infinity. Even degree is the same way. Since it's positive, they both point up. So that's the really kind of thinking thing. Okay, the last thing that I have on your homework today is you are going to actually do a little bit of maybe factoring. So I think I'm going to skip this next one here, and we're going to make this number 4. And this is our last one. The last part of your homework, and I think I gave you 2 or 3 problems from this one. It says, find the zeros of the function algebraically. We just talked about that we don't know how to solve these using what we did last year with PRZs and dividing zeros out and a bunch of stuff. Which means all of these problems you're going to have to be able to either factor, complete the square, or the quadratic formula. Complete the square and the quadratic formula only work when it's an x squared. So if this problem has something bigger than x squared in it, step 1 is you're going to have to be able to factor something out. And so I just want to do one of these to remind you that we could actually do this problem. Could I factor anything out of this problem to begin with? A 5 and an x? And if I factored a 5x out of that, I would get x squared minus x minus 2. And then some of the ones on your homework today, they might not be factorable, but I think lots of them are. But then you can try to factor this again, right? quadratic formula if you prefer, but you can't do the quadratic formula until you have x squared, x, and a constant. But I think this is factorable. What multiplies to give me 2, that subtracts to give me negative 1. Negative 2 plus 1. Now it's back to what we just did. If I asked you to find the zeros of this, could you do that? Yeah, you're just going to set each one equal to 0. So 5x equal to 0. It just gives 0. This one I'm not going to do the work there. Set that equal to 0. I'm going to get x equals 2. And x equals negative 1. Questions about that? Big thing today is in behavior and practicing with those zeros. Your homework is what's on the assignment sheet, but I think I wrote a few notes here. I wanted to make sure because I know the directions are kind of weird on this. 3, 6, 18 through 36 multiple to 3. Number 24 is not factored for you, and it wants you to find the zeros, but we're going to look at that tomorrow with the graphing calculator. So number 24, you're just going to do the in behavior because unless you have a graphing calculator, you're not going to be able to find the zeros of that. But the rest of them you should be able to do. Like, I can tell you that, like 27, the directions say describe the polynomial using limits of x goes to infinity, but just do the in behavior the way that we did it. But that's the only one. 24 is the only one that I was kind of worried about you would freak out about. I guess I gave you 2 graphing. Number 3